Alrighty, in this video we're talking about sampling distributions. Now this stuff is pretty weird, but it's one of the most powerful things we can do with statistics. Up until now, we've looked at single things, and in this example we'll be looking at like a can of Coke. It's distributed normally, and it's going to mean in this case is 380 mils and a standard deviation of 3 mils. So we're used to doing things that are just like one object. But my question is, what if we have like a 24 pack of cans of Coke? Like, how is that distributed? We'd expect the mean to be a lot bigger because we've got a lot more cans. So mean of X, which is just a single can, is 380. So let's think about the mean of S24. Now S24 means the sum of 24 cans, or in other words, the mean of the 24 pack of Coke. And as you might expect, is literally just 24 times the original mean. 24 times 380. And we can work out what that is. 24 times 380 gives you that number there, which is 9120. So that's pretty much as you would expect. You get 24 cans, the mean times is by 24. Standard deviation of a can of Coke is 3 mils, but then the standard deviation of S24, you might expect it to be 24 times the old standard deviation. But it's not actually that. So the reason for that is, you can imagine this is going to be a lot more spread out. There's a lot more variance because there's a lot more cans. But when you have each can in your list of 24 cans, yes, there's going to be more variance because you got heaps of cans that you're playing with. But the cans that go up and down will sort of cancel each other out in a sense, a little bit. So there's not going to be as much variance as like a single can times 24. It turns out that you have to times it by the square root of the number of cans, root 24. Bit weird, but it's just how it works. So that's where this formula is coming from. So you can see Sn we define as the sum of n things, and in this case n was 24. So the new mean is n times the old mean, so like 24 times the old mean is what we did. And the new standard deviation is like root 24 times the old standard deviation. And depending what n is, you'll just use a different number there. All right, so that's sort of what it is. We can get an approximate for this. So root 24 times 3, we'll just see what that is. Times 3 gives us 6 root 6, but probably better off to get an approximate there, 14.697. So you can see the standard deviation is bigger than what it was before, but it's not like crazy big as you might have expected originally. So the next one here is sort of asking about the average. So rather than looking at the sum of the entire weights, we're looking at this new thing called X bar 24. Now what X bar 24 means is you take your 24 pack of cans and then you look at sort of the average weight across that packet. So X bar 24 is also distributed normally. Now the weight of a single can is 380 mils. And indeed, the new mean is also 380 mils as well. So it doesn't change. So if you look at all 24 cans and then you take the average of those, it should be the same as if you take the average can volume. It doesn't change that. But your new standard deviation, so the mean of X24 is just the same as the mean of X, which is 380. But your standard deviation of X24, well, it's the original standard deviation, but you have to divide it by root 24. And that sort of comes from this formula here. So we have two things that we talk about. Sn is sum of n samples. And Xn is sort of average of n samples. So it's like you've taken a 24 pack, but divided by 24 to get the numbers back to a sensible amount. Anyway, this ends up being, so the original standard deviation of 3 over root 24, which, let's work that out. 3 divided by square root 24 gives you 0.612. So we can see that it is a lot less spread out, way, way, way less spread out. So if you want to look at here's 380. If you want to look at the distribution of X, it's probably looking something like that. But if you want to look at the distribution of X24, it's looking something like that. So the standard deviation is getting lower. And again, that's because you've got all these cans canceling each other out. I often find the S a lot easier to understand than the X, but that's the idea behind this stuff. All right. Next one is just a straight up theory question. So X is distributed normally like that. X8. Now, X's should always have bars on top. X8 is distributed normally. The mean doesn't change, but you've got 3 over root 8 is your new standard deviation. So this would be like you've got cans of Coke in an 8-pack, for example. So if you want, what you can do is get an approximate for 3 over root 8, which we'll do. And we'll do S to D to change that back. 1.061 is the new standard deviation. Again, you can see it's a lot smaller than the original standard deviation of 3. And the distribution of S8, so S8 is distributed normally. So you're going to get 12 times 8 and then 3 times root 8. So S8 is distributed normally. So 12 times 8, we'll see what that is. That is 96. And then 3 times root 8. Oops, 3 times root 8 is going to be 8.485. So that's our new distribution there. You can see it's more spread out than the original, but it's not like 8 times more spread out. All right, now this one's another practical example. So the capacity on this elevator is 1,600 kilos, and it says 21 persons on the elevator. So basically the average weight of each person. So the way you calculate an average is you get the sum, like you basically get the total weight of all the people divided by the actual number of people. And we know that the average, so we know the total weight is 1,600 at maximum, and the number of people is 21. And then this is the average weight. So if we do 1,600 divided by 21, that gives us sort of the average weight that we're not really allowed to exceed. 76.190. So basically this elevator is saying like, yeah, you're allowed to have 21 people in there as long as the average weight is no bigger than 76. So if you put 21 people who are all 100 kilograms in there, that's going to be 2,100 kilograms, and you're going to have issues with your elevator there. If you actually look at most elevators in the real world, you'll find the average weight is actually kind of scarily low compared to the real average rate of people. But anyway, next thing here. Suppose the mean weight of an Australian is 72 kilograms and the standard deviation is 10. You want to calculate the chance that a person is over 76 kilograms. So this is a standard normal CDF question. Let X be the weight of an Australian. X is distributed normally with a mean of 72 and a standard deviation of 10, which is fairly accurate. I'm pretty sure I Googled those numbers. So probability that X is bigger than 76 is going to be approximately equal to, and this is where we do the normal CDF. So if you're on a Texas, it's going to be in your second distribution, normal CDF. If you're on a Casio, it's going to be menu, stats, distribution, norm, NCD. But at any rate, our lower is going to be 76. Up is going to be a whole bunch of 9s. And standard deviation we said was 10. And our mean was 72. So we'll pop all those numbers in. The chance that an individual is over 72 kilos, 76 kilos is 0.345. So sort of the scary interpretation of that is 34.5% chance of doom. Crashed elevator. All right. Now, have a think about why that's wrong before I just tell you. But the reason why it's wrong is because this is the chance that a single person is over 76 kilos, 34.5% chance. But if you've got 21 people in an elevator, the chance that collectively they have an average over 76 is actually going to be a lot lower than this. So we'll do that calculation. All right, so somebody wants to calculate the chance of 21 people. Is it higher or lower? The answer is going to be lower probability because you would need all of them to be quite a bit bigger than the mean on average. So attempt to calculate the probability. So S21 is the distribution we want. It's distributed normally. Now, the mean of S21 is going to be 21 times the mean of a single person. It's 21 times, we said 72 was the mean of a single person. And if we try and work that out, 21 times 72 times 72 gives you 1512. So the average weight of a group of 21 people is 1512 kilograms, which you'll notice is a lot lower than 1600 kilograms. And that's because like the average weight of each person is 4 less, so collectively they're quite a bit less. Now, if we want the standard deviation of S21, it's going to be root 21 times the standard deviation of X. So we'll see what that is. So it's going to be root 21 times, and I reckon the original standard deviation was 10. So that gives you 45.826. kilograms. And then S21 is now distributed normally. 1512 is the mean and 45.826 is the standard deviation. So let's just work that out. So we're going to do another normal CDF, and we're going to be calculating the probability that S21 is bigger than that capacity of 1600. So what's the chance that the elevator has too much weight in it, essentially? So our lower is going to be 1600. Our upper is going to be a whole bunch of 9s. Our standard deviation is that number we've just worked out, 45.826. And our mean is going to be 1512. Make sure I got that right. Yep. All right, now let's execute and figure out what our probability is. All right, so our probability is 0.027. All right, so what we actually have is a 2% chance of overweight limit, which is a lot less scary than the original answer of 34% chance. Although, to be honest, if you're building a real elevator, you wouldn't want there to be a 2% chance of it crashing. You would want there to be a very, very low percent chance of it crashing. And the way that you do that is you'll probably bump that number down to 20 persons rather than 21. The other thing that I want to show you as we finish up is an alternate method you could use to do this. We could look at the distribution of X21. That's distributed normally. The mean is the same as a single person, which was 72 kilograms. So the mean is 72, and the standard deviation is going to be the original standard deviation. The original standard deviation was 10, but we need to divide it by root 21, and that gives us this X21 distribution. So that's 2.182. And if I work out the probability of the X21, so the probability the average weight of each person is greater than 76, that should hopefully give me the same number here, 0.027. So let's see if that actually works. This is just like an alternate method to work out the same problem, and it shows you how the X bar thing and the S thing are actually related. So again, we're just going to do 76 as our lower. The upper will be the same. The standard deviation will be 2.182, and then the mean will be 72. Execute that. 0.033. Something's obviously gone a little bit wrong there. 0.033. It's about the same. I suspect, and I'm not going to get too bogged down in it, that that's just due to rounding with the standard deviations. That could be slightly wrong there. 2.182. Yeah, it's probably just a rounding thing there, but you can see 2.7 and 3.3% are very similar. In theory, this should actually give us the correct answer. I think probably the issue is, 76.190 kilograms. If I'd use that as my lower instead, 76.190, that will probably give me a much better idea of what the probability should be. Yeah, 0.027, 76.190. Now I can see the importance of rounding because now that answer actually really does match. So you can do it with the S21 method or the X bar 21 method, but either way you're going to get the same probability, 2% chance of doom.